So I'm very excited to be here and share my view on how we can design deep learning techniques for program synthesis, and especially on recent progress of language models for code. So in general, the goal of program synthesis is to enable users with different levels of coding skills to automate this coding procedure so they can really benefit from all these advances of programming tools. So basically, instead of writing all the code ourselves, we want to ask the machine to automatically generate some programs for us. So this will also accelerate the coding process for professional programmers. Program synthesis has empowered numerous real applications. So one common use case is to translate natural language into programs. And this is the space where large language models have really shown a great progress recently. So on the slides, I'm showing a demo from OpenAI Codex. And also right now, people know their most recent model, ChatGPT, also shows this very impressive capability of writing code. So here, basically, users just need to write down the functionality they want in natural language, and the model is able to generate the code correspondingly. For many applications, the natural language alone might not be precise enough to fully describe the code the users want. So in many cases, we can also add some additional information in other formats. So one of such formats is called input-output examples or unit tests. So in this case, these input-output examples will further specify the intended execution behavior of the program. So on the slides, I'm showing one picture of our DeepMind AlphaCode project. So I was working on this project when I was at DeepMind. So this is about some problems in competitive programming. So in these cases, typically the program description includes both the text and also some input-output examples. So later on, I will discuss some core techniques behind this work and show how the model can leverage this additional information to achieve more impressive performance than using the natural language alone. So in some cases, our program might not be just operate on some token sequences, and it might need to operate on structured input data, such as tables. So this is important, especially for data processing and analysis. In this talk, I will also discuss my work Spreadsheet Coder, where we design a learning-based model to automatically generate formulas in the spreadsheet context. So in this space of designing learning models for code, actually we can see that this model scaling is already becoming an important topic for recent work. And this is the same both for processing code and processing text data. So on the slides, I'm showing two families of models, the Codex from OpenAI and Palm Coder from Google. So we can see that without much change of the underlying model architecture, by simply scaling the model from hundreds of millions of parameters to the largest 5 billion model of the Palm model, so the model performance improves from nearly useless to highly impressive. This model scaling also shows that for these state-of-the-art language models, they are actually trying to unify the text and code data by representing the code as token sequence. So if we think about it in this way, then such a very impressive performance gain might be a bit surprising for us as human programmers, because actually our coding process is very different from writing text. In particular, we definitely do not just write a code from left to right. Typically, we will have a very careful reasoning process about the code structure we want. We will decompose the whole program into different pieces and think about the building block in the whole program, and also actually think about the syntax structure in the actual implementation. So given that the current language models can just achieve very impressive generation performance in both text and code without actually considering some unique properties of code, one natural question I want to discuss in today's talk is whether model scaling is just all we need, and is it still necessary to think about some new techniques to further advance this field? To discuss this topic, here I will present two of my works emphasizing both on real applications and on this fundamental algorithmic reasoning performance of these models on solving challenging coding problems. So I will first discuss my work Spreadsheet Coder, where we show that we can develop a relatively small model which can perform well in the production use of these program synthesis applications. Then in the AlphaCode work, we will show that simply scaling out the model does not necessarily give us more intelligence coming from the model, and we still need something else to really achieve good performance on solving the challenging programming problems. So let's get started with the first part about Spreadsheet Coder. Here is a demo to illustrate how Spreadsheet Coder works. So basically, when the user types in this assignment operator in a Google Sheet, we know that the user is trying to write a spreadsheet formula. So in this case, the model will be activated to provide some formula suggestions. As you can see, here the users do not really write down very explicit descriptions about the formulas they want. But still, our Spreadsheet Coder model is able to infer all the user intents from the tabular context. So there's no explicit descriptions in natural language or other formats. The spreadsheet language can support a wide range of formulas for data processing and analysis. So in the previous demo, we have seen these examples of numerical calculation. Besides that, Spreadsheet Coder also supports the generation of conditional statements, formulas for table lookups, etc. In total, there are around 100 operators supported by Spreadsheet Coder, which is a pretty comprehensive set. Although the spreadsheet language itself is not that complicated compared to those popular programming languages like Python, C, Java, etc., still, this automatic generation of formulas can really improve the user experience a lot, and it have a lot of benefits. Like what has been shown in the news release, it can fill those math formulas and also make the data analysis easier and quicker, and also help the models to reduce the burden of memorizing all the spreadsheet language syntax. Predicting spreadsheet formulas in this tabular context has introduced some new challenges that are not really emphasized by these recent large language models themselves. So the first challenge is about understanding the structure of the input data. So in many cases, the spreadsheet formulas do not always operate on a single row or a single column. Instead, those cell ranges can cover multiple rows and columns at the same time. So to help the model to better understand the data, it is important to really represent the input as in its tabular format. The second challenge is to model the long-range dependency. So on the slides, I'm showing an example where there can be over 10,000 rows in a single table. So in this case, it is very important to understand the dependency of different cells, even if they are very far away from each other. To address these major challenges, we designed this Spreadsheet Coder architecture with the focus of modeling the structure of both the input and output. So at a high level, the architecture has two key components. One is the encoder, where it represents the input data as a semi-structured table. Another component is the decoder, and we designed a two-stage decoding process to consider that the difficulty of predicting the spreadsheet operators and the cell ranges can be different for different contexts. In total, this model has around 100 million parameters. So this is a relatively small size compared to recent large language models for code. In this presentation, I will focus more on the encoder design to address the previously mentioned challenges. So because the spreadsheet tables can be pretty large, so it is computationally expensive or intractable to encode all the cell values at once. To address this challenge, we designed this block-wise encoding, where we split the entire table into multiple blocks according to its tabular structure, like we can split it into row-based blocks or column-based blocks. So in this way, we can encode larger tables with this block embedding. However, with this block-wise embedding alone, if we consider the representation of each cell, then it only incorporates the context within the same block. So to further model the long-range dependency across different blocks, here we design a one-dimensional convolution layer. For example, on top of the row-based block embedding, we can design a column-wise convolution, where the convolution layer will span across multiple blocks. So after we apply this convolution operation, then in the final table embedding, these cell values representations will incorporate the context both inside the same block and across different blocks. For evaluation, here I'm showing some results we published in the research paper, and later on we definitely have some new results on user study, which cannot be fully published here. So from this smaller scale of data, which includes around 20 million row formulas, we can show that this modeling of structures can really allow us to achieve much better results, where this metric is computed by making sure that for the predictive formulas, both the spreadsheet operations and the cells are correct. So this top one accuracy of around 42% is pretty good in the sense that here the formulas prediction doesn't really utilize any explicit signals from the users. And we believe that if we add some more interfaces, allowing the model to communicate with users in some natural language forms, then this performance can be further improved for generating those more complicated formulas. Now I will discuss the second part, which is more about the fundamental programmatic reasoning performance of these language models with the AlphaCode project. Recall that in AlphaCode, we consider this competitive programming setting where the model input includes both text description and input-output specification. And here, the text description can be pretty long and complicated. It can be not that intuitive even for the top human programmers. So this is why they are called competitive programming. Then, given this description includes both text and input-output samples, the model is required to generate the corresponding code. So here I'm showing an example of the Python solution correctly generated by the AlphaCode model. So if we look into this code, we can see that there's no direct mapping between the problem description and output code. So the model doesn't really only need to understand the problem description, but also need to come up with an algorithm to achieve a good compute complexity and solve the task in the required time. So for such a very challenging task, what we can achieve with the best models right now? So we evaluate the AlphaCode model on the Codeforces platform. It participates in 10 competitions where there are over 5,000 human programmers per contest. We use an ensemble of 41 billion and 9 billion models, and we allow the model to submit 10 solutions per problem. Among these 10 competitions, our AlphaCode model can achieve an average ranking of around a top of 54%. And if we consider this rating overall, it is among top 28% of all the Codeforces users. So clearly, this is still far below the top human programmers. But we consider it as an important milestone because it shows that these models are really able to solve some very highly non-trivial and challenging programming problems and demonstrate its algorithmic reasoning capability. So given these results, one question arises. So the question is whether model scaling can just solve the problem. Remember that we have these previous models which can be over 100 billion large or even like 500 billion parameters. To answer this question, here I'm showing some scaling curves by comparing different AlphaCode models with different sizes. If we compare these curves, we can see that the performance gain becomes less and less significant with larger models. Especially if we compare 9 billion and 41 billion models, they are like pretty similar, although the 41 billion model is nearly 5 times larger than the 9 billion models. In particular, if we focus on this data point, where all the models are only allowed to generate 10 programs, then actually no model achieves decent performance with such a few samples. This means that for the 10 final submissions, they actually come from much more initial samples from the model. And in practice, we ask the model to sample 1 million programs per problem. So here is an overview of the AlphaCode framework, including data collection, model training, and also sampling and evaluation. Here, I will emphasize this process of filtering and clustering in the model inference procedure, where we show that we need to leverage the program execution, which is crucial for achieving a competitive performance. So first, for the filtering procedure, given that 1 million program candidates, we will execute all these programs on the given input-output samples in the problem description, then filter out those samples that do not pass the test. Note that for these coding problems, passing this example test alone is insufficient to show that this solution is correct, because there are also some hidden tests to like understand whether this program submitted by the participants can also pass some larger scale tests and generalize beyond these given example tests. This simple filtering alone can already eliminate over 99% of the samples. So on the other hand, it also shows that the current language models still have some flaws because it cannot even pass the example tests that are already given as part of the model input. Then, if we consider 1 million initial candidates, then 1% still includes around 1,000 programs. Then, to select 10 out of these 1,000 programs, we have a second process called clustering. And again, we are using program execution. Recall that we have these hidden tests for programs which are not seen to the models. So we train another separate model to generate new test inputs so that we can have a better understanding of the code's semantic meaning. So note that for these generated inputs, we do not know their ground truth outputs because we don't have the ground truth programs. So basically, what we'll do is that we will execute these sample programs on all these generated inputs and cluster all programs with the same outputs together. So here we can assume that programs in the same cluster are semantically equivalent, given that we have enough generated test inputs. Then we will sample one program from 10 largest clusters. So the idea here is that the correct programs can cluster better together, while the wrong programs will be wrong in different ways. Here I'm showing some results to demonstrate that this filtering and clustering procedures is really crucial. If we compare this red curve with all other curves, we can see that if we do not do any filtering, then the model performance is nearly zero, even with 1 million programs. So this shows that still right now, the model sample efficiency should be further improved. Then we can see that this clustering procedure can actually provide much more performance gain than simply scaling out the models if we compare this performance from 9 billion to 41 billion, and also with the 41 billion model using clustering. In addition, we also evaluate our model on another benchmark called apps. So this is another benchmark for competitive programming. So here we are showing that the AlphaCode model can outperform those other GPT models that are much larger, including the 12 times larger Codex model. So this will be about the projects I have been discussed. Looking forward, I believe right now it's just the start of these language models for code. Also, there are already very impressive achievements we've seen, and there are a lot of challenges and future opportunities. The first is about modeling the hierarchical structures. So this is not just about understanding the structures of the input, but also about how to really model these hierarchical structures of the output code so we can go beyond this next token prediction for more complicated programs. The second challenge is sample efficiency. We want the model to really give us the correct prediction in one pass instead of relying on many predictions and have to then in this case we have to select. We have to spend a lot of time in this prediction selection. And fundamentally, we really want these language models to go from short instruction following to the true algorithmic reasoning, so the model can better understand the underlying algorithms and to perhaps can also think about better implementation than us as humans. So this is the end of my presentation. Thanks a lot for listening, and also I'm happy to take any questions.